Jai Hind to all of you. I am Dr. Ritish Kumar. I am going to give the presentation or give the lecture on the topic of micro magic T and directional coupler. This is the topic of the second unit, which is in the subject of microwave and radar engineering. So let's begin with the topic. What is the magic T and directional coupler? So before starting the magic T, we need to understand what is the T. There are different kinds of Ts available in the microwave radar engineering subject. So these are the passive component devices. So uh, as we all are aware about the what is the active component, passive component. So similar terminology we are using here, the passive component devices. Let's begin the waveguide T. So here you can see here it is looking like a T junction, right? It is looking like T form either in the place of in the first kind of and second kind of. But by looking by the field orientation point of view, these both are the different waveguide T. So based on the orientation of fields such as electric field and magnetic field, we need to characterize these as a E plane T and H plane T. E represents the electric field and H represents the magnetic field. So suppose if I remove this section from this T, then you can observe here this is a simple kind of waveguide we have here. So if you attach a secondary waveguide from the primary waveguide, then we have a kind of T form. Again, if you remove this section from this waveguide from this T, then you can observe here this is simple kind of waveguide here. Now how can we differentiate this E plane T and S plane T? So look at here, the orientation of E field. This arrow is representing the electric field orientation in both both E and S plane T, right? So this this arm is known as main arm. This, or we can say this waveguide is known as main arm or main waveguide, while this attached waveguide is known as secondary waveguide or auxiliary arm, we can say here. So look at here, the orientation of E field. We can say this E field is oriented either in the positive. Suppose if I draw this is X and this is Y, right? So can I presume that this this electric field is oriented towards the positive Y direction and negative Y direction? So we can say this is bipolarized electric field. While in the case of, similarly we have in the case of another kind of T junction, the field is oriented in the positive Y direction or negative Y direction, right? So look at here, if you draw the electric field orientation, you can observe this is a metallic boundary and field is oriented towards the negative Y direction. So this boundary has the tail of the arrow. So always you need to consider the tail of this arrow in this direction, right? If you and this arm is having the direction of arrow in this downward direction. So now after passing this field through this auxiliary arm, the orientation of E field change from this orientation to this orientation. While because why? Because the arrow is touching at this boundary, so always the arrow is touching this boundary. So the orientation is changes from downward to upward with the help of this auxiliary arm. Suppose why we are calling this E plane T? Because if you look into the elective E plane, suppose what is the kind of E plane? Suppose as we know from the Pointing vector theorem, if the propagation of the wave is in the direction of z, so with the help of Pointing vector theorem, P is equal to E cross H, Pz is equal to x y, right? So if I say the field is in the direction of y, then always we have the field of magnetic in the direction of x to have a propagation in the z direction. So we can say in the case of the plane, in terms of plane, we can say the yz plane is known as E plane, while the case of xz plane is known as uh, H plane, right? So if I say this plane is parallel to the yz plane, while in the case of this arm is parallel to the xz plane, right? So in the terms of terminology, how can we define the third arm of auxiliary arm is parallel to the plane containing E field, right, of the TE10 mode in the main waveguide. So what is the TE10 mode? TE10 mode is the fundamental mode of a waveguide where one is representing the half wavelength variation in the x direction, while 0 is representing the half wavelength variation in bidirection. So there is no variation in the case of bidirection. So this is the fundamental mode of the rectangular waveguide TE10 mode. So these two plenty are complementary by nature, as we have seen. The E field in the plane is the orientation of field is parallel to the E field, while in the case of H plane T, the auxiliary arm is parallel to the plane containing H field of the TE10 mode, right. So here you can see the in the main arm the field is oriented in the bi-direction, right. So again the this arm always, this boundary always has the has the arrow. So you can observe here the direction of arrow is same in the auxiliary arm as well, right. So where we can use the waveguide T, where we have where we need to take the power take the different kind of power with the help of power divider or power combiner. So in the microwave engineering, we need to make a power divider with the help of magic T or E plane T or H plane T as well. So it can be used in the case of power divider and power combiner devices. While as you can see, if I combine these two plane T, E plane T and H plane T simultaneously uh, in a single device, that device is known as magic T, right. Here we have written here a combination of E plane T and H plane T is called as hybrid T. Now come to the next slide, E plane T. So you can see here the this is a 3-port device, port 1, port 2, the flow port 1 and port 2 is known as the, this is main arm, or this one is a port 3 is a kind of secondary arm or auxiliary arm we can say, or also we can say side arm, or main arm is also known as collinear arm as well. So look at here, uh, this is a port 1, port 2 and port 3. Here we are considering the port 1 as an input port, while the port 3 and port 2 are known as output port. If you give the power at input port or transmit the power through port number 1 and the field is oriented towards the y direction, so what should be the orientation of E field in the auxiliary arm or collinear arm. So you can look at here. Here the this boundary and here this boundary has a arrow or so throughout this boundary you can observe here the arrow is drawn over this boundary. So the field is, and with the help of this boundary, this the tail of this the tail of the arrow is touched towards this boundary. So so you can observe here this arrow in the positive y direction, and this arrow is minus negative y direction, right? So with the help of this auxiliary arm you can change the direction of electric field from upward to downward direction, or you can say the phase shift in between this input port to the output port is exactly 180-degree phase shift in between these two. So now now what will happen if you treat these two, if you treat the port 3 as an input port and port 1 is and port 2 is acting as a output port. If you deliver, if you delivered the if you deliver the power through a port number 3, what will you get at the output port? So again you can observe here this is the in the same the phase of the port 1 and port 2 is having the 180-degree phase shift. So this is the cross sectional view of this wave E plane T, and if you look into the 3D view you can observe here this is a T E plane T, and why we are calling this a E plane, because this plane is the E plane, because this plane is having the electric field and this arm is parallel to this plane, right? That's this plane, that's why we are calling this is a E plane T, right? Now this is a scattering matrix for this passive device, that is E plane T, and you can observe if you give the if you give the power P1 at port number 3, then you will have a P1 by 2 at this approximated at these two port, because power is equally divided in port number 1 and port number 2. We by using these two orientation we have this scattering matrix, and you can observe here this is 1 by root 2, 1 by root 2, 1 by root 2 and 1 by root 2. This is because of the having the um, power divider. So this is a scattering matrix that you need to remember it. Now the H plane T. So similarly we have the H plane T here. You can look at here. This is a E plane T, and this is a plane of E plane, and you can observe here this auxiliary arm is perpendicular to this plane, or we can say this auxiliary arm is perpendicular to the E plane while the parallel to the H plane. That's why we are calling this is this is T, this is a H plane T, and corresponding the scattering matrix of this T is written over here. Similarly we have in the case of E plane T. So again if you give the input power through port number 3, you will have the power in the same phase at port number 1 and port number 2 respectively, and this is a kind of H plane T. If you combine these two plane T as E plane T and H plane T, you will have a magic T. Next is the waveguide magic T here. Now you can see here this is a E plane T and this is a H plane T. That's why we are calling this a E arm and this one is a H arm, right? So if you here this you can see this one is the E plane right, and this one is the H plane, right? Now, why we are calling this magic T, we will learn here. So now, uh, uh, here port number, this is a 4-port device we can see here. Now, port number 3, why port number 3 is also known as summation or subtraction port, according to the phase given at port number 1 and port number 2 in this waveguide, in this T, right. If you give the um, suppose if you give the if you give the power at port number 1 and port number 2 simultaneously, and the field orientation in this port number 1 is like towards the bi-direction, positive bi-direction in both port number 2 and port number 1 as well. So, in the E arm, at the junction point, this field is in the direction of this way, while this field in the direction of this way. So, at port number 3, you will have the field in the opposite or 180-degree phase shift with each other. So, so these two fields are cancelled out, are cancelled out with each other. So, we can say this port is acting as a subtracting port. It is represented by delta, while in the case of H arm you will have the E field in both from port number 2 and port number 2, you will get the field in the positive bi-direction. So, this uh, uh, so at this port you will have the summation of these two field. So, this port is known as summation port here. Now, if you change the phase of the port number 1 and port number 2, suppose if I change this field orientation from 180 degree with 180 degree phase shift. So, this is these two fields are opposite in phase. So, at last you will get the summation of the E field at port number 3. So, this port is replaced by summation port, while this port is replaced by subtraction port, right. So, by changing the orientation of E field, we can change the E arm and H arm from subtraction port to the summation port and vice versa, right. So, the suppose in terms of power, we can say if you give the power at port number 1 is P1, while at port number 2 is P2. So, you will get the power at port number 3 is P1 minus P2, while at port number 2 you will get the power P1 plus P2, right. So, this is about the magic T here, right. So, you can see here, if two waves of equal magnitude and same phase are fed into port number 1 and port number 2, the output will be 0, right. At port number 3, if you, here we if P1 is equal to P2, then you will have delta is equal to 0. If a wave is fed into port number 4, it will be divided equally in port number 1 and port number 2 of the collinear arm that will not appear at port number 3. This is about the power combiner and power divider case. Now, if a wave is fed into port number 3, it will produce an output of equal magnitude and opposite phase at port number 1 and port number 2. The output at port 4 is 0, that is S43 and S34 is equal to 0. Similarly, we have S12 and S21 is equal to 0. This is about the waveguide magic T. Now, this is a scattering parameter of the waveguide. So, this is due to the condition of third and fourth, right? Now this is a scattering matrix that you need to remember it, and because it is a power divider and combiner, that's why we are taking the 1 by square root of 2, and plus minus sign is uh, giving the phase orientation of the E field here. So this is a scattering matrix that you need to remember it. Now the second topic is the directional coupler. What is a directional coupler? So this is a 4-port device. You can observe here 1, 2, 3, 4, and these ports are known as port 1 port 1 is acting as an input port, and 2 as throw port, and coupled port 3, and fourth port is an isolated port. This is a reversible device. So if you change the port number 2 and port number 3 as a 1 and 4, so you will get this port number 1 as 2 and port number 4 as 3. So you can see here what is the formula for coupling. Coupling is always having from port number 2 to port number 3. So this is a kind of how much power is coupled from port number 3. You can see here C is equal to 10 log P1 by P3. If you find the directivity, then you need to consider the port number 3 and port number 4. So you will get the directivity of the directional coupler, that is P3 by P4. Isolation is always having from port number 1 and port number 4. That relates the thing that how much power is isolated from port number 1 to port number 4. So this is the formula is 10 log P1 by P4. Insertion loss is always from port number 1 to port number 2, that is input to throw port, that is 10 log P1 by P2. So with the help of directional coupler, this is a kind of another device from where we can have the different kind of power received from port number 2, 3, 4, as you have if you give the power at port number 1, right? So the commonly used symbols for directional couplers and power flow conventions. Two-hole directional coupler. This is a diagram for two-hole directional coupler. You can observe here there are hole number 1 and hole number 2, and this two-hole directional coupler having the distance between two holes is exactly equal to lambda g by 4, and it is represented 2n plus 1 lambda g by 4. If you consider n is equal to, then you will have L is equal to lambda g by 4. This should be the quarter wavelength distance. Why? Because here you can see this is a primary waveguide, port 1 and port 2, and port 3 to port 4 is a secondary waveguide. So with the help of two holes, we have connected these two waveguides, primary waveguide, secondary waveguide, with each other in such a way so that you can have the added power at port number 4 and port number, and cancel power with each other at port number 3. This can be happen only in the case of if these two holes at a distance of should be at a distance of lambda g by 4. Why? Because if you give the power at port number 1, so there is chances this is a throw port, this is a there is chances to have the power from port number 2, 3 and 4 simultaneously. So what will happen if you have the distance between the holes lambda g by 4? So if you give the power at port number 1, so direct power you can receive at port number 2, and in the case of port number 4, you will have the option either power flow in from this hole to this port, and from second hole to this port. In the case of port number 3, there are two possibilities to receive the power from hole number 1 from this way, and from hole number 2 to port number 3. So if you look at it here, so how much distance is traveled from port number 1 to port number 4 while passing through hole from hole number 1 and hole number 2, right? This is 2. So this port is acting as a added port. Why? because the traveling distance from both hole are same. That's why we call this is a added port. While in the case of at port number 3, how much distance travels from port number 1 from passing through hole number 1 and hole number 2. So there is a difference from how much distance is more from port number 1 to port number 3. This is a total distance is lambda g by 2, right? If this is lambda g by 2, if you find the phase from this the travel distance 2 pi by lambda g, so it will cancel out, 2 cancel out. So these are both travel phase is opposite in phase 180-degree phase shift. That's why both the power will be cancelled out at port number 3. So you will not have any kind of power at port number 3. That's why we call this port number 3 is a isolated port. And this is scattering matrix for the directional coupler here. So you need to remember this scattering matrix here. So I think these two topics, magic T and directional coupler, to clear to all of you. Thank you very much.